In this video, I'll be introducing the idea of a tangent space on a smooth manifold. So first of all, what are some intuitive examples? Well, you understand the concept of tangents. If you're given some smooth curve like this, you're given some points on that smooth curve, then you can create the tangent line that goes through that point along that curve. And you create that tangent line by doing the derivative. You're given this one-dimensional curve, you're able to generate at any point this one-dimensional line by using derivatives. And similarly, if you're given a surface, like a sphere, if you're given any point on that sphere, then around that point you're able to generate a tangent plane. Now, how do I determine this tangent plane? Well, one way to do this is by taking directional derivatives through that point. So I could take the cross section through that point and then look at the normal one-dimensional derivative of that cross-sectional curve that is generated. And so if I take that derivative, that tangent, I can generate a vector like that. And then if I take a cross-sectional derivative that goes like that, cuts towards me, then the cross-sectional derivative there, directional derivative there, is going to look like that. And then these two tangents will act as basis vectors for the rest of the plane. And so what you should take out of this is that if you're given a one manifold, you're able to generate a one-dimensional vector space at any point using some concept of derivatives. And at any two manifold, you're able to generate a two-dimensional vector space at any point using two different concepts of derivatives. So you have two separate derivatives you need to be able to take. And so our intuition tells us that if we're given a smooth manifold M, which is of dimension n, then the tangent space at some point P of that manifold is going to be an n-dimensional vector space based on some notion of derivatives. How do I go about generating this idea in general? Because we can't just do like these very visible vectors like we did on these tangent planes and tangent lines. What we have to actually do is generate abstract vectors. And the way we're going to generate those abstract vectors is by making them the derivatives. And so if we make our vectors the derivatives, and those derivatives are just defined as operations, then we can define the operations on any general manifold and thus have our TPM. What do we start with? Well, I say we start with a very, very basic manifold, namely Rn. For the purposes of demonstration, I will use R2. What I need to do is I need to be able to pick any point. Let's call it A. What is the tangent plane at A? Well, R2 is flat. There's no curves, there's no dips, and so this flat plane, any tangent to it will just be itself. And so, given any point A tangent vector to A is literally just any vector in R2. So any such v that is in R2 will generate a tangent vector of A due to flatness. Well, I can go ahead and say that every tangent vector to R2 is just going to be some pair where you're given a base point, A, and some vector that stems off of it, V. Let's go ahead and call this symbol a geometric vector, V sub A. Now I can extend this idea to general Rn. Because each one of those multidimensional real spaces is also going to be flat, their corresponding tangent hyperplanes are going to be flat in themselves too. And so what I'm going to do is define a concept called Rna, and this is going to be the collection of geometric vectors at that point A. This is going to be analogous to the tangent space, but because this isn't our purely algebraic way of viewing it, it is not our tangent space yet. And so this Rn sub A is just going to be equal to the set of A Cartesian product Rn, or the collection of vectors VA. What we need to be able to do is transfer this idea, where at any point you're given a tangent vector, which is just in Rn2, we need to transfer that to some abstract definition of a derivative. Well, the way we do it, and it's the same way we would do it on these, well, remember what I said about the sphere. We needed to take directional derivatives. And so our way out of this is by doing directional derivatives. Namely, I'll define the operator d at one of these geometric vectors VA, and because it's a directional derivative, we have to apply it to some function f. Now this f is going to be a function that takes you from Rn down to R. Now the reason we're doing that is because, if this is your input plane, this is your output plane, this is the concept of a surface. That function is going to be represented by some surface, and you know how to take the directional derivative of a surface. What is this going to be equal to? Well, let's go ahead and start with a very intuitive definition of it. Namely, d on dt at t equals 0 of f of a plus tv. How on earth is this intuitive? Well, let's go ahead and think about it. What is happening with this function as t changes? Well, when t is 0, this is just f of a. And so in a way, a is your starting point. So you start at a, and then when t increases, what you're doing is slowly moving from a along in the direction of v. When t is 1, you literally have a plus v, which is this point represented right there. And so what you're wanting to do is, moving along this vector, take the derivative at your starting point. And so that's the directional derivative, but we can write this in a simpler way that you've probably heard of before, namely by the multivariable chain rule. This is going to be equal to the sum for I equals 1 to n being the dimension of R, and it's going to be equal to, well, del f on del xi, so the partial derivative of the outer function, applied to a plus tv, and you evaluate this at t equals 0. Well, what is that? Well, that's going to be a plus 0 times v. So that's just a. And then we multiply this by d on dt, evaluated at t equals 0, of the inside, which is going to be a plus tvi, where each one of these vi's is the coordinate of v at that point. So what is the evaluation of this derivative? Well, a is a constant, that goes away. T goes to 1, and vi is a constant, and so that's 1 times the constant vi. So you're just left with vi. You evaluate it at t equals 0. That doesn't do anything because there's no t in the expression, and so you just get this formula, which, using Einstein's summation convention, is going to be equal to vi times del f on del xi applied to a. And Einstein's summation convention says that this index is on the top, this index is on the bottom, it's in the denominator, and so what you do is you sum over all the possible values for that index. Whenever you see an up index and a bottom index of the same variable, then you know to sum over all possible values of it. This probably aligns with the definition you've probably heard of a directional derivative, which is v, a vector, times the gradient of f applied to a. And so that's the dot product there. What are some properties of this operator? Well, it actually has all the standard properties of a derivative. Namely, it is linear. It's not only linear, it also has a product rule, or the Leibniz rule. So if I do d evaluated at VA, and I apply it to f times g, and evaluating this uses this definition of the operator. And I won't prove it, it's very, very easy. It's just the fact that this d on dt has the product rule as well. So this is going to be equal to dva of f times g evaluated at a plus dva at g times f evaluated at a. This is just the chain rule, and you're evaluating it at your base point a. Those are the two signifying characteristics of a derivative operator. It's linear and has the product rule. How about we just make that the definition of the derivatives that we're going to be using for the tangent space? And so what we're going to define is this idea of a derivative operator in general. It's going to be called a derivation. So what we define a derivation to be is going to be some map, W, which takes in a smooth function on M, which will take you from M down to R, because we did there, and it will take one of those functions and output some element in R itself. Now we say that this map is a derivation at some point P and M if it's linear and you have the product rule.
So W of F times G is equal to W of F times G of P plus W of G times F of P.
And this is where the value of P, of which is the derivative at, actually matters. Remember the reasoning here. We started with Rn and the general tangent vectors on Rn, and we were able to create from each of those tangent vectors a derivation operator. And then we just generalized that derivation operator to all smooth manifolds. And so what I want to show is that it would be a good idea to say that the tangent space at some point P of a manifold is the collection of derivations at P. So what I'm going to do to prove to you that this is a good idea is show that one, it is a vector space, and two, that there's good reason to believe that it's an n-dimensional one. First of all, you can very easily show that this is a vector space. Namely, if I want to do W plus W prime, the summation of two derivations, when I apply it to some function f, I'm going to define it to be just Wf plus W prime f. In a similar way, if I want to do a scalar c times W applied to f, then that's going to be defined to be c times W applied to f. And then it's very, very easy to show that not only are each of these operators derivations, but that they follow the axioms for a vector space. And so what we've done is take this generalized version of a derivative and turned it into a vector space. Now it's very, very easy to show some other facts about these derivations, namely that W of a constant, C, is 0, and that if we have it that F applied to P is equal to G applied to P is equal to 0, then that means W of F times G is equal to 0. Those are both infinitely easy to prove. This one, you just use the product rule. This one, you can use linearity. So I know it's a vector space, and I know it has some of the properties I might associate with derivatives. How do I know that these derivations form a vector space that is n-dimensional? So the proof on a general manifold is actually difficult, but it's super easy to prove this on the real numbers. So let's go ahead and do that. Theorem 2 is going to be that the association of these geometric vectors to the derivation that we derived before is an isomorphism, which takes you from Rna into Ta-Rn. So it takes you from the geometric vectors into the tangent space. And also remember that this is very easy to define a vector space structure on, because it is just a vector space, but you add in a little base point into a pair. And so you can define, VA plus WA to just be V plus WA. And similarly with scalar multiplication. And so what this theorem is basically confirming to us is that this association with the tangent vectors directly and intuitively on Rn are actually one-to-one with these operators, and thus we have an even greater reason to suspect that this is a good definition of the tangent space. In the next video, we will actually prove, that the tangent space on the general smooth manifold is n-dimensional. But for now, we're going to have to settle with just the real numbers. Now, if you look at this directional derivative and you use this definition, it's very easy to prove that this is, in fact, a linear map. So I'll just assume that. Now, because it's a linear map, let's go ahead and prove that it is injective and surjective. I'm going to start with the proof that it's injective. Now, because this is a linear map, it being injective just means that the only value that gets sent to 0 is 0 itself. So what we have to prove is that if dVA applied to f is equal to 0 for all f, then that means that VA was just 0 at A. How do I go about proving that? Well, what I want to do is use the definition of the components, the component form of this definition. Namely, that this is going to be equal to VI times del F on del XI applied to A. That's equal to 0. The reason I'm writing it like this is because if I can find a special function f that basically singles out a single one of these coordinates for each coordinate, then I can prove that each coordinate of v is equal to 0. This special function is going to be xj, which will be a map from Rn to R by definition, and it is going to be the projection onto the jth coordinate. xj of a1 to an is going to be aj. And so this projection onto the jth coordinate is exactly what we want, because if I do the derivative of xj in respect to xi, what is this going to be equal to? If j is different from I, you can look right here. There is no instance of the ith coordinate showing up. If I and j are different, it is 0. But if I is equal to j, well then you just have this single variable showing up. And so when I take the partial derivative, that's just going to be 1 when I is equal to j. This function, which is 0 when I is not equal to j, and 1 when I is equal to j, I will refer to as the Kronecker delta function. Why is this what we want? Well, because when I is not j, it's going to be 0. And so it cancels out that coordinate of v. But when I is j, it's 1. And so it leaves just that coordinate of v. And so you single out that single coordinate of v when you input this function. And so if I do dVA applied to xj, that's going to be equal to vi times del xj on del xi. Because it's 0 for all values different from j, it's just going to be equal to vj. And by this previous fact, we know that this has to be equal to 0. This index was arbitrary, and so we showed that each individual coordinate of v is 0. And so we've proven that only the 0 vector maps to the 0 operator. Now let's go ahead and prove surjectivity. Why is it surjective? Well, this one's a bit harder, but we use the exact same principle. In this one, we applied the map xj in order to isolate the single coordinate of v. And so let's go ahead and say we have some w, which is in the tangent space. Then I will define the vector that will map onto it, v, which is in R and A geometric vector. I will define as its coordinates, vi, is going to be equal to w applied to xi. By the same principle, if you apply the xi in, it'll be able to single out your single coordinates vi, and then it'll be able to reverse engineer it. How do I prove then that d at this v, defined in that way, at A, is equal to w? Well, I basically have to prove that when they're applied to a function, they're equal to each other for all of those functions. Well, I'm going to create a representation of any general smooth function that will make it super easy to prove this. Namely, by Taylor's theorem. This is a specific form of Taylor's theorem you've probably never seen before. If I have time, I'll create a video where I prove this form of Taylor's theorem. The way you can define it is by f of a plus the sum from I equals 1 until n of del f on del xi applied to A times xi minus ai. All right, that's our main part. And then we add on another sum, which will be a dual sum, a double sum, for ij equals 1 until n of xi minus ai times xj minus aj times an integral, which we don't actually have to care about. Now the reason we don't have to care about that integral will become apparent when we actually take w of this function. By Taylor's theorem, we know that any smooth function can be represented in this way. Where do we go from here? Well, let's go ahead and apply w to f. F of a, that's a constant, that's 0. Because w is a linear operator, I can go ahead and move it inside that sum. That is a constant times a function, and so I can just leave the constant alone and apply it only to the function. So when I apply it to that, I will get w of xi minus w of ai, but ai is a constant, and so it's just 0, so I'm left with this. W of xi, by definition, is vi. Great! But remember this extra term. What am I going to do with it? Well, it's a linear operator, so I can move it inside the sum, and I'm just doing w of xi minus ai times xj minus aj times some integral. What do I do with this? Well, I'm going to group it into two different parts that you're multiplying. I'm grouping it into xi minus ai and xj minus aj times the integral. Now, let's go ahead and look across to proposition 1. If we have two functions where f of p is the same as g of p and they're both equal to 0, then w of f times g is equal to 0. Well, our base point's a, and so if I do x equals a, ai minus ai is 0. If I plug in x equals a, I get aj minus aj is 0. And so both of these are 0 at a. And what that tells you, you're doing the multiplication of two things 0 at a, and so that all zeroes out. You're doing the sum of a bunch of zeros, and you're just left with the formula you wanted. And so, by the coordinate representation, this is just going to be equal to dva applied to f. And so we proved that every one of these operators has a corresponding geometric vector where the directional derivative is equal to it. And so it's surjective, we proved that it was injective, and so this is a bijective linear isomorphism. Now that we've proven that there is a direct one-to-one correspondence between geometric vectors and these operators, that tells us that these derivations don't just form a vector space, but they also form one that's analogous to our idea of a tangent space in Rn. And then, in the next video, we will prove that it's also analogous in manifolds. And so, our tangent space at some point p of our manifold is just going to be the collection of derivations at p. That's how we will define it. Now, let's go ahead and say we have some geometric tangent vector VA. Just go ahead and ignore A for now. Well, I know that it's going to be representable as VI times EI using the Einstein summation convention there. So we're summing over all of them, where VI is its coordinate and EI is the basis. And I know that EI is going to be the vector which is 0 at every place but the ith coordinate. What's another way of stating that? Well, another way of stating that is that EI at the jth coordinate of this vector is going to be 0 if j is different from I, and 1 if I is equal to j. Basically meaning that it's going to be equal to delta ji. And so what you get is that the coordinates of each of these basis elements is the Kronecker delta function. Why is this important? Well, because these EIs are a basis of Rna, then if I map it along this isomorphism into the tangent space, then the images of these basis elements will form a basis. That's just a property of isomorphisms. And so if I take D at EI evaluated at A, this collection for I equals 1 to n will generate a basis of the tangent space on Rn. By definition, this is going to be equal to del on del xj evaluated at A times Eij. This is by the coordinate representation of this operation and Einstein's summation convention. But as we discussed before, Eji is the same as delta Ji, and that means that this will just single out the single component del on del xi for which I is equal to j. All the other ones will go to 0, 0 multiplied by anything 0. You single this out. And so what you get is that the collection of partial derivatives, this is for I equals 1 to n, this collection of partial derivatives is a basis of the tangent space on Rn. And what we will prove in the next video is that the collection of some analogous idea of partial derivatives evaluated at the point P for I equals 1 to n is a basis of the general tangent space, TPM, for the n-dimensional manifold M. As a recap, what we did was we started with the intuition of tangent spaces as n-dimensional vector spaces based on derivative operations. Then we used the discrete and very easily definable example of the tangent space on Rn, and then we created an equivalence of this very intuitive notion of geometric vectors into a derivative operator, which could be extended abstractly to all manifolds. Once it was extended abstractly to all manifolds, then we proved that this correspondence between geometric tangent vectors and the tangent vector operations is in fact one-to-one. They are the same exact idea. Then we proved that partial derivatives are a basis of the tangent space. Next video, we will prove this fact about general manifolds and introduce another differential operator. Anyway, that's it.